March 4, 1944, RAF Boxted Airfield, Essex, England. Rows of P-51 Mustangs stand under a grey morning sky. The grass runway is wet from overnight rain. Ground crews in oil-stained coveralls attach long, unfamiliar tanks beneath each wing. The tanks are dull grey and slightly uneven in texture. They appear fragile, more like packaging than aircraft equipment. A clipboard note identifies them as 108-gallon Type A drop tanks. The tanks are made not from metal, but from paper, glue, and resin. Workers from a nearby cellulose factory designed them as single-use fuel containers. The outer surface is coated with varnish to resist moisture. When filled, each tank weighs approximately 700 pounds. Its empty weight is less than 50. The innovation reduces drag and increases range by nearly 40% compared to earlier designs. At 7 o'clock hours, pilots of the 354th Fighter Group received briefings inside a canvas tent. Their mission: escort 8th Air Force bombers striking targets in the Berlin area. Until this week, no fighter escort had reached the German capital and returned. Mustang range had been limited to central Germany. Previous attempts required mid-mission refueling or diversion. The commanding officer reads from a printed order: P-51B aircraft equipped with 108-gallon auxiliary tanks will proceed to accompany bomber formations to Berlin. Pilots review fuel charts. One officer, Captain James Stewart, marks his flight plan in pencil. The notation RTB, possible with drop tanks, appears in the margin. Mechanics secure the tanks with quick-release shackles. Each line connects to the Mustang's main fuel system through a valve beneath the wing. The fuel mixture must be carefully balanced to prevent vapor lock. A technical sergeant performs a final check with a hand pump and pressure gauge. At 8:30, engines start across the field. Merlin engines produce a uniform roar under the low clouds. Ground control issues clearance, blue flight, climb and proceed to rendezvous point over Southwold, 15,000 feet. By 9 o'clock, the formation crosses the English coast. Below, the North Sea reflects scattered light through a cold haze. Each Mustang carries the new tanks, now filled with high-octane aviation gasoline. Within 90 minutes, they will cross into hostile airspace. Over the radio, bomber crews report sighting their fighter escort at altitude. Little friends in sight, moving to cover position. The phrase confirms visual contact with the P-51s. At 10:30 hours, near Magdeburg, German radar plots multiple formations inbound from the northwest. Jagdgeschwader 11 is scrambled from Jüterbog. Interceptors climb to intercept. Luftwaffe controllers anticipate the fighters will soon turn back, as they had in previous missions. But this time, they do not. The Mustangs maintain formation. The external tanks, though crude in appearance, continue feeding fuel to the main system. Range and endurance exceed all prior tests. By noon, contrails extend eastward beyond the Elbe River. Allied pilots can now accompany bombers to Berlin and still return to base. For the first time, Germany's heartland lies within continuous Allied fighter reach. At Boxted, base engineers record the experiment's success in a maintenance log. One entry reads, "Paper tank satisfactory. No failures reported. Recommend mass issue." The simple cellulose tank, dismissed by some as temporary or unsafe, has proven decisive. Its lightweight, low cost, and disposability make it ideal for rapid production. This moment marks the beginning of long-range escort dominance in the European air war. The success at Boxted will soon spread across every Mustang-equipped squadron in the 8th and 9th Air Forces. The war's geography has changed by paper, glue, and fuel. By early 1944, Allied strategic bombing depended on endurance. The 8th Air Force had learned this through loss. Without escort, bomber formations faced severe attrition beyond the Ruhr. Luftwaffe fighters exploited predictable withdrawal limits. Most P-47 Thunderbolts and early Mustangs lacked the range to cover Berlin or Leipzig and still returned to England. Intelligence summaries from January 1944 noted, current fighter coverage ends near Hanover. Bomber losses east of line unacceptable. The report prompted a directive from 8 Fighter Command, development of extended-range auxiliary systems mandatory. The Air Technical Service Command analyzed prior solutions. Early metal tanks, derived from naval stores, had proved too heavy and costly for mass use. Aluminum shortages limited output. Rubberized tanks caused vapor pressure irregularities and occasional leaks. Each alternative presented maintenance or supply complications. At the same time, the British Ministry of Aircraft Production was investigating cellulose composites. These materials, made from laminated kraft paper treated with phenolic resin, could be molded at low temperature and high speed. They required no strategic metals. Production could be subcontracted to civilian firms using paper mill equipment. In late 1943, engineers at the British firm Mullinus Limited proposed a mold paper external tank for Spitfire and Mustang variants. Their prototype, weighing less than 45 pounds empty, passed stress and leakage tests under simulated flight conditions. The project gained attention within the Allied Technical Liaison Committee, where U.S. Army Air Forces engineers reviewed the findings. Major Benjamin S. Kelsey of the USAF Materiel Command recorded in his notes, composite tank shows favorable weight-to-volume ratio. Recommend field evaluation. The evaluation proceeded at Wright Field, Ohio. Within weeks, the design was adapted for North American's P-51B model, with U.S. specifications for quick-release suspension and standardized fuel coupling. Parallel developments occurred at the British Air Fighting Development Unit, Duxford. Reports from November 1943 indicated successful operational trials. 108-gallon paper tanks function normally through climb, cruise, and transfer. Leakage minimal. While effective, the design remained controversial. Pilots expressed skepticism. Paper was associated with fragility, not reliability. Ground crews feared structural collapse under aerodynamic stress. To address concerns, a series of vibration and pressure tests was conducted at the Royal Aircraft Establishment, Farnborough. Each tank endured simulated flight turbulence for 50 hours without rupture. By February 1944, authorization for limited operational deployment was granted. The contract was issued to several British and American suppliers, including Boata Lloyd and the British Glue and Chemical Company. Each facility could produce several thousand units monthly. Cost became a decisive factor. A metal 108-gallon tank cost approximately $75 to manufacture. The paper version, less than $10. For a campaign requiring thousands of sorties, the savings were substantial. The disposable nature also simplified logistics. Empty tanks could be jettisoned over the channel or enemy territory without recovery efforts. In operational terms, the tanks allowed Mustangs to escort bombers beyond the previous cut-off line. This changed not only flight routes but also Luftwaffe response patterns. German fighter groups were forced to engage farther east, burning precious fuel before reaching Allied formations. From an engineering standpoint, the cellulose tank was a compromise between endurance and expendability. Its introduction demonstrated that wartime innovation did not always depend on advanced metallurgy or complex design, but on material efficiency and mass production adaptability. The Allied command recognized this by mid-1944. The once derided paper tank had become an operational standard, enabling the full strategic reach of long-range escort missions. Initial test flights began in January 1944 under controlled supervision at Wright Field, Ohio. Engineers monitored fuel flow, pressure stability, and temperature differentials between internal and external tanks. Instrument readings confirmed steady transfer rates from the paper tanks into the main fuselage system. No vapor lock or sediment contamination was recorded. Laboratory analysis examined chemical interactions between aviation gasoline and the tank's resin coating. The results indicated less than 1% absorption after 72 hours of exposure. Structural deformation occurred only when tanks were left unsealed for prolonged humidity. Under flight conditions, they remained intact. Operational testing continued with the 354th Fighter Group in England. Maintenance officers compared the cellulose tanks with aluminum types across multiple missions. Reports logged between February 2 and February 25, 1944, noted fuel feed stable. Structural performance satisfactory. Recommended for wider issue. The tests revealed an additional advantage: the tank's disposability reduced aircraft weight after emptying. Once fuel transfer completed, pilots released the tanks at altitude, restoring full maneuverability. In combat zones, this allowed immediate transition from escort to engagement mode without compromising safety. Detailed field observations followed. Lieutenant Harold Comstock recorded in his after-action report, at 18,000 feet, tanks jettisoned without incident. Aircraft performance improved markedly. No drag or instability observed. The engineering documentation listed several innovations. Each tank contained a laminated wall thickness of approximately 1/4 inch, using alternating craft layers bonded with phenolic adhesive. The inner liner was impregnated with fuel-resistant resin, applied through pressure curing at 160 degrees Fahrenheit. A vent assembly and feed pipe were fitted through a small aluminum collar, ensuring compatibility with existing Mustang fuel lines. The manufacturing process was simple yet precise. Paper sheets were formed on rotating molds, dried in heated chambers, and coated with varnish. Each completed unit passed a 2-hour static pressure test at 8 psi before delivery. Rejects were burned for waste recovery. The entire production cycle required less than 48 hours per tank. Data from the first 100 missions using cellulose tanks showed a negligible failure rate. Out of 3,200 tanks deployed, only 9 exhibited leakage or structural failure. Comparative statistics from aluminum tanks showed higher defect ratios due to weld fatigue or corrosion. The discovery phase also addressed aerodynamic behavior. Wind tunnel experiments conducted at North American Aviation confirmed that the lighter tanks produced less turbulence beneath the wing. The smooth curvature and absence of weld seams minimized drag coefficient values by approximately 3%. By March 1944, combined British and American evaluations concluded that the cellulose tanks were fully operational. Memoranda from the U.S. 8th Air Force Engineering Section stated, "Composite external tank system approved for all P-51B units effective immediately. Prioritize distribution to forward bases." Logistical implications were immediately apparent. Shipping manifest showed that a single cargo ship could transport over 15,000 paper tanks, a capacity 3 times higher than equivalent metal versions. This enabled mass deployment throughout the United Kingdom by April. From a technical perspective, the cellulose tank represented a low-cost, high-volume solution to a strategic endurance problem. It demonstrated the integration of civilian manufacturing methods into military logistics. The innovation required no new alloys, only the reconfiguration of peacetime paper molding machinery for wartime efficiency. The data collected during these early trials formed the basis for full-scale operational planning. Each flight log, each material test, each post-sortie report verified the same conclusion, that paper fuel tank was not an improvisation. It was a scientifically validated engineering advancement, achieved through material pragmatism and repeatable performance. By late March 1944, combat data confirmed what engineers had only theorized. The cellulose drop tank had transformed fighter operations over Europe. Escort coverage now extended from English bases to Berlin, Leipzig, and Merseburg, and back. Mission debriefs described reduced bomber losses and higher strike completion rates. 8th Air Force statistics compiled on April 10 recorded a notable change. Average bomber loss per mission had dropped from 9.1% in February to 3.2% in March. Analysts attributed the reduction directly to continuous Mustang Escort presence throughout target approach and withdrawal phases. At the operational level, the results were visible in both navigation and tactics. With the 108-gallon tanks, Mustangs could cruise economically at 250 miles per hour for over 4 hours. Their effective combat radius exceeded 750 miles. When combined with internal fuel reserves, total range surpassed 1,600 miles. This capability allowed pilots to accompany bombers deep into central Germany, an operational envelope previously considered impossible. Flight crews soon adopted new patterns of engagement. Mustangs flew high cover during the bomber's inbound leg, then dropped tanks and descended to intercept climbing Luftwaffe fighters. Reports from JG-26 and JG-11 noted increased American fighter presence at altitudes once thought unreachable for escorts returning from long-range missions. German intelligence summaries from spring 1944 recorded the shift. One captured document, later catalogued by the Air Ministry, read, "Enemy single-engine aircraft now accompany heavy bombers throughout penetration zone. Extended endurance confirmed. Countermeasure uncertain." At the engineering headquarters in London, Allied planners reviewed this evidence. Memoranda circulated under the heading Results of Long-Range Fighter Program. The findings emphasized endurance over performance. Range, not speed, as determined outcome of deep penetration operations, one line stated. By April, the cellulose tank had become an integral element of every strategic raid. Factories in Britain, Northern Ireland, and the United States operated around the clock. Each P-51 departing East Anglia carried 2 of these tanks beneath its wings. The units were filled to capacity minutes before takeoff, sealed with wax-coated caps, and checked for leaks by ground engineers. Pilots gradually abandoned skepticism. Operational reliability overcame initial distrust. In interviews recorded by the Army Air Force's Public Relations Office, several pilots described the change simply, "They work." That phrase appeared repeatedly in the transcripts. Field reports detailed further benefits. The paper tanks produce minimal shrapnel when struck, unlike metal tanks which could fragment dangerously. Their low radar return reduced detection by early warning equipment. The light composition also allowed safe detachment near populated areas without significant ground hazard. Industrial administrators recognized these properties as strategic multipliers. In correspondence between the British Ministry of Aircraft Production and U.S. Air Technical Service Command, one note summarized, "Disposable auxiliary system has permitted maximum aircraft utilization with minimal resource expenditure." By May 1944, when the Allied bombing offensive reached peak intensity, nearly every long-range escort sortie relied on cellulose technology. The results were conclusive. German air defense units faced continuous Allied air presence for the first time. Luftwaffe fuel consumption rose dramatically as fighters were forced to remain airborne longer, awaiting attacks that never withdrew early. The realization extended beyond combat performance. It demonstrated how minor technical adjustments could generate disproportionate operational advantages. The cellulose tank was not a symbol of improvisation but of systematic efficiency, an industrial adaptation that changed the logistics of aerial warfare. The war's strategic balance began to reflect this new endurance. Long-range escort capability ensured that no target within Germany remained beyond Allied reach. What began as an experiment in material economy had redefined the geography of the European air campaign. By mid-1944, the cellulose drop tank had become a core element of Allied air logistics. Production and distribution records show an industrial network operating across 3 nations. Britain supplied mold components and varnish coatings. The United States manufactured coupling hardware and fuel valves. Canada provided bonded paper stock and adhesive resins. Each factory followed identical specifications approved by the Air Technical Service Command. Monthly output exceeded 100,000 units by June 1944. Manufacturing data compiled at the Ministry of Aircraft Production listed average production time per tank at 14 labor hours. A single plant in Kent produced 2,000 tanks per week using rotary molds and drying ovens. Finished units were stacked in lightweight crates, each marked "Do not expose to moisture before use." Transportation efficiency improved significantly. A single rail car could carry 1,200 paper tanks, compared to 400 metal tanks of equal volume. Warehouses near RAF airfields at Boxted, Debden, and Leiston stored over 25,000 ready units at any given time. American bases in East Anglia maintained identical reserves. From a logistics standpoint, the cellulose tank solved two persistent problems: metal scarcity and aircraft turnaround. The tank's low cost eliminated the need for retrieval or maintenance. Ground crews attached new tanks within minutes of aircraft recovery. As a result, sortie rates increased by 18% between March and July 1944. At the operational level, the system expanded Allied flexibility. The extended range allowed Mustangs to support operations in France, Belgium, and Western Poland without forward deployment. Escort squadrons based in England could protect bombers striking rail yards, refineries, and aircraft assembly plants across the continent. Intelligence summaries from SHAEF, dated June 1944, cited direct effects on German industrial output. Continuous bombing of fuel installations made possible by sustained escort coverage, one report stated. German aircraft production declined 35% between March and August 1944. Intercept frequency over Western Germany fell accordingly. The cellulose tank also aligned with broader Allied production philosophy, decentralized manufacture using non-critical materials. Wartime coordination boards encouraged small firms to participate. Paper mills, furniture makers, and packaging companies were temporarily converted to military contractors. The process demonstrated how civilian industry could integrate into total war without extensive retooling. Statistical records preserved at Wright Field reveal the materials economy. Total wartime expenditure for cellulose tanks amounted to approximately $20 million, compared to an estimated $180 million for equivalent metal units. This ratio underscored the advantage of material substitution under resource pressure. The tank's disposability presented environmental challenges, but wartime directives classified jettisoned tanks as expendable ordnance. Recovery teams documented widespread dispersal across northern France and the Low Countries after raids. Civil affairs officers reported minimal damage or fire risk due to the material's limited combustibility once emptied. Strategically, the cellulose tank became part of the doctrine of sustained penetration. Continuous fighter presence altered Luftwaffe engagement tactics. German pilots could no longer exploit bomber withdrawal points. Radar operators detected Allied aircraft over Berlin well after the bomb runs, indicating escort coverage deep into return corridors. The design also informed post-war thinking about modular logistics. Later jet-age drop tanks, made from aluminum and fiberglass, followed similar disposable principles first proven by the cellulose prototype. Within Allied planning documents, the paper tank symbolized a convergence of science, manufacturing, and logistics. It represented the material dimension of strategy, the ability to translate simple industrial adaptations into decisive operational advantage. By summer 1944, the Allied air offensive had achieved continuous reach from the British Isles to the eastern borders of the Reich. That reach was sustained, in part, by a structure of paper and glue, an innovation never intended for permanence, yet fundamental to victory. After Germany's surrender in May 1945, technical evaluation teams from the U.S. Army Air Forces compiled final assessments of wartime equipment. Among the listed innovations, the cellulose drop tank received a brief but definitive summary: performance satisfactory. Production highly efficient. No redesign required. Surviving examples were rare. Most had been used, discarded, or destroyed. The few that remained were collected from storage depots and test facilities for documentation. At Wright Field, engineers dissected a pair of intact tanks to study degradation after prolonged exposure. The analysis confirmed that the laminated kraft paper maintained 85% of its original tensile strength after 1 year in controlled conditions. The war's end shifted attention from production to interpretation. Technical historians within the Air Materiel Command categorized the cellulose tank as an auxiliary systems innovation. Its function, though simple, demonstrated the principle of sufficiency, achieving operational goals through minimal resource input. Air Force logistics officers cited the tanks in post-war lectures as examples of low-value material yielding high-value effect. The official History Army Air Forces in World War II, published in 1948, mentioned them in a single paragraph but emphasized their significance in extending Allied reach to Berlin and beyond. Civilian industries that had produced the tanks reverted to peacetime manufacture. Paper molding facilities resumed packaging and consumer goods production. Yet the knowledge gained from wartime processes influenced later industrial methods. The bonding techniques developed for the tanks evolved into early composite fabrication systems used in automotive and aviation materials through the 1950s. At North American Aviation, engineers studying jet aircraft design noted the strategic value of external, disposable components. The P-80 Shooting Star and subsequent F-86 Sabre incorporated metal and fiberglass drop tanks following the same principle first tested with cellulose. These later systems achieved higher fuel capacity and aerodynamic refinement but retained the same logic, expendable endurance. In Britain, the Ministry of Supply retained technical papers from the cellulose tank project as part of its non-metallic materials archive. Reports highlighted the cooperative nature of the program, involving small factories, independent chemists, and industrial laboratories. It stood as an example of adaptive production in total war. Veteran accounts from Mustang pilots reflected retrospective appreciation rather than sentiment. Most recalled the tanks only as a tool that worked. Colonel Don Blakesley of the 4th Fighter Group summarized it in a post-war interview: "They gave us range. Range won the air war." His statement aligned precisely with statistical analyses published years later. The paper tank success had no direct technological descendant in the modern era, but its logic persisted. Every long-range mission, from the Cold War to present, relied on auxiliary fuel concepts first proven by this wartime experiment. In the broader history of engineering, the cellulose tank occupies a small yet instructive position. It exemplified how necessity redirected design priorities, from complexity toward practicality. Wartime urgency favored what could be built fast, cheap, and good enough to work once. By 1945, more than 2.5 million cellulose tanks had been produced. Each served a single flight, often lasting less than 8 hours. Yet collectively, they enabled operations that accelerated the collapse of the Luftwaffe and the destruction of German industry. When the 8th Air Force reviewed its final campaign summaries, analysts concluded sustained escort coverage was decisive. Extended range made total air superiority possible. Thus, a wartime invention born from paper and glue, ephemeral in substance, became an enduring lesson in the power of material economy. Its quiet efficiency helped close the distance between England and Berlin, and with it, the European air war itself. Post-war evaluations conducted between 1946 and 1948 by the U.S. Army Air Forces Engineering Division placed the cellulose drop tank within the category of transitional materials technology. Analysts noted that its contribution was not in advanced performance, but in the demonstration of logistical adaptability under wartime constraints. The engineering files recorded clear metrics. Average unit failure rate, 0.28%. Mean time from order to delivery, 96 hours. Production cost per gallon capacity, 9 cents. These figures confirmed its efficiency when compared to any metallic equivalent. A comprehensive report titled Composite Structures in Airborne Applications summarized its operational effect. The cellulose external tank enabled a 40% increase in fighter radius, producing measurable impact on strategic bombing success rates. This report was distributed to the newly formed U.S. Air Force in 1947 as a case study in resource optimization. British technical analysts reached similar conclusions. The Royal Aircraft Establishment's 1946 memorandum stated, "The mold paper auxiliary tank represents the most efficient non-metallic fuel system produced under combat conditions. Its simplicity allowed rapid manufacture by non-specialist labor, minimizing training requirements." From an industrial policy perspective, the cellulose tank exemplified how wartime governments coordinated civilian production toward military output. Archival documents from the Ministry of Aircraft Production describe the process as an exercise in distributed efficiency. Paper manufacturers, varnish suppliers, and adhesive chemists collectively achieved performance standards normally associated with precision aerospace components. The innovation also carried economic lessons. A comparative study by the U.S. Bureau of Aeronautics showed that the cellulose tank program consumed less than 0.03% of wartime aviation budgets, yet contributed directly to a measurable decline in bomber loss rates and fuel logistics expenditure. It represented an instance where minimal cost yielded strategic outcome. From a materials science perspective, the cellulose laminate anticipated future developments in fiber-reinforced composites. The adhesive and resin bonding methods later informed experimental work in glass fiber aircraft components. Several engineers who had participated in the wartime tank program joined post-war research projects at Convair and Boeing. Their experience with lead bonding under variable humidity became valuable in developing early non-metallic aircraft panels. The concept also influenced post-war logistics design. The use once, discard principle became a foundation of modern ordnance and fuel systems, from missile casings to auxiliary pods. The cellulose tank demonstrated that strategic endurance could be achieved without permanent hardware, provided that manufacturing was scalable and predictable. Military historians analyzing the European air campaign consistently linked the introduction of long-range escort capability with the decline of German air defense cohesion. Luftwaffe sortie rates, according to captured OKL data, decreased 22% between March and August 1944. The correlation with continuous escort coverage was statistically evident. The cellulose tank's success also reflected a cultural shift in engineering thinking. It favored design economy over prestige. In contrast to complex mechanical breakthroughs, it embodied wartime pragmatism, used the simplest possible means to achieve decisive effect. The same idea resurfaced decades later in defense production philosophy, lightweight composites, modular systems, and expendable platforms. Modern aerospace design literature frequently cites the cellulose tank as an early example of resource-directed innovation, where material scarcity catalyzed creativity rather than constrained it. In retrospect, its greatest achievement lay not in its form, but in its timing. Introduced when Allied air strategy demanded endurance over complexity, it provided precisely what was needed, no more, no less. The simplicity of the solution made it universally adoptable, bridging the gap between experimental design and frontline necessity. By the close of the decade, the cellulose drop tank had become a footnote in aviation history. Yet within that footnote resided a central truth of modern warfare: technology's value is measured not by its permanence, but by its ability to deliver results at the moment they are required. By the early 1950s, the cellulose drop tank had already vanished from inventories, but not from doctrine. Technical manuals and staff college syllabi still referenced it as an example of wartime efficiency through unconventional materials. The Air Materiel Command Summary of Logistics Experience, 1939 to 1945, described it as the most effective non-recoverable equipment item developed during the conflict. In 1952, the U.S. Air Force Research and Development Board included the cellulose tank in its retrospective study on economy in aircraft supply. The report concluded, the mold paper auxiliary tank proved that temporary structures can fulfill permanent strategic functions. It became a case frequently cited in lectures on wartime innovation and industrial adaptation. Material scientists studying post-war composite technologies recognized parallels. The cellulose laminate shared core principles later formalized in synthetic fiber composites, directional layering, resin impregnation, and low-temperature curing. In this sense, the wartime paper tank was not an endpoint, but an early prototype of modern bonded structures. In Britain, several surviving molds were preserved at the Royal Aircraft Establishment, Farnborough, as instructional artifacts. Accompanying documents included wartime production notes, resin formulations, and tensile strength data. These materials later informed early aerospace research into reinforced polymers used in civil aviation by de Havilland and Handley Page. From a historical perspective, the cellulose tank symbolized a transition between industrial eras. It connected traditional manufacturing, based on manual labor and bulk material, with the emerging paradigm of lightweight composites and modular production. Its development marked the moment when wartime necessity forced scientific methods into everyday industry. Archival analysis of Allied air strategy consistently lists the tank among the lesser-known yet crucial enablers of total air superiority. By providing endurance to the P-51 Mustang, it allowed bomber formations to operate with near-continuous escort protection. Post-mission summaries from 1945 described the shift in concise terms: range equals reach. Reach equals control. The tank's invisibility in popular history reflected its function. It was never designed to be remembered. It left no wreckage of significance, no emblem, no symbol. Yet it altered the operational geography of Europe's skies more effectively than any single airframe modification. Military logisticians in later decades revisited the cellulose tank when evaluating disposable fuel systems for jet aircraft, missiles, and unmanned platforms. The same principle, minimal weight, maximum output, single use, remained consistent. In 1961, a RAND Corporation memorandum on cost-efficient military production cited the tank as an instructive precedent for expendable design philosophy. The industrial legacy extended beyond aviation. Paper bonding methods first perfected for the tanks reappeared in civilian sectors, packaging, insulation, and even early fiberglass hulls for marine craft. Technical continuity between wartime cellulose work and post-war composite industries was well documented in trade publications from 1949 to 1957. Within the historical record, the cellulose drop tank illustrates a recurring pattern: material improvisation reshaping strategic capability. It reflected a moment when the boundaries between science, engineering, and production blurred completely under the pressure of total war. The result was a weapon not of destruction, but of endurance, invisible, functional, and absolute in its effect. The legacy endures in data, not debris. Every subsequent aerial endurance record, every long-range strike mission, follows the same logic first proven by paper. The lesson remains straightforward: technological progress often begins where resources end. When the last official wartime report on Allied aviation logistics was published in 1955, one brief line summarized the cellulose tank's place in history: a temporary measure, permanently instructive. 80 years later, its importance remains measurable in the simplest fact of all: without it, the P-51 Mustang might never have reached Berlin, nor returned to tell the story.